Hi everyone, we are starting our last unit. This is a unit that normally would have been covered before the AP exam. However, with distance learning, we didn't get to it, so we are going to do a brief preview of it before you move on in your math careers. First section we're looking at is how to find the area between two curves. However, a lot of you already demonstrated this understanding as I did assign a question about this topic on one of those AP practice exams. So it is fairly intuitive. To find the area between two curves, you take the area of the upper curve and subtract off the area of the lower curve. So that's what we're going to be doing today. For our vocab, that is essentially what all of those words say. I also have two diagrams for you because we're not just going to be looking at it in terms of the x-axis like we normally do. We can also look at area in terms of the y-axis. That's our second diagram here. So when the function is an x equals in terms of y, then what we do is we take the function that is further from the y-axis and subtract the function that is closer to the y-axis. So that's that second equation we've got going on right here. For our first practice, we will look at these in terms of x so we can get used to it, and then we'll look at the more challenging ones that are in terms of y. Determine the area between y equals x squared and y equals x cubed. So we have a diagram here, but we need to know which equation is the one that is the red one, the one that's further from the x-axis, because that's the one that will go first, and then we'll subtract the green equation from it. Our red equation is x squared, and our green equation is x cubed. Now for the definite integral, we also need to know where it meets. So you can either set them equal to each other and solve, or with these it's pretty intuitive. We know that if x is 0, that both equations will be true, and if x is 1, both equations will be true. We're looking at this area in terms of the x-axis, so we're looking at our bounds in terms of the x values as well. So the area between these two curves will be the integral as x goes from 0 to 1 of our upper curve minus our lower curve. Notice I used parentheses and I'm using a dx as I was grading those AP practice exams. Those were two notation errors that were missed a lot. And for AP, you lose a point for every notation error like that. So make sure that you get those parentheses and that dx. This one, pretty straightforward to integrate. They're both just power rules. So adding a power to x squared, we get 3, and then either multiplying by the reciprocal or dividing by 3. Same thing with our x cubed, adding a power and then multiplying by the reciprocal. And this, we don't need a plus c when it's a definite integral. We're going from 0 to 1. So we're going to sub 1 in for x, pretty easy to cube, and raise 1 to the 4th power. And then we subtract parentheses with those definite integrals. Be careful that you don't lose the distributive property that you're going to get when you subtract an expression. In this case, subbing 0 in for both, we just get 0. So our area is 1/3 minus 1/4. This one I would expect you to be able to find a common denominator and subtract pretty quickly. However, you can also use that fraction button on your calculator to help you out. Remember, it was alpha y equals, and you'd be able to enter those fractions in. I know a lot of you love decimals. I do not. They're not exact values. The fraction gives you the exact value. So we have 4/12 minus 3/12, which gives us an area of 1/12. I do want you to put units squared for all of the answers for your area, just to remind you that that's what we're finding when we're doing this integral, is the area under the curve, and in this case, the area between two curves. Our next example, we do not have a picture for. You will be using graphs for a lot of these, and Desmos is an awesome resource if you don't have a graphing calculator. It is also an awesome resource when we get to the ones that are x equals, because our graphing calculators don't have that capability. So I have these two equations on Desmos already. It is helpful if you sketch this picture in your notes and sketch the pictures in your assignment as well. Another nice feature of Desmos is that if you just tap, it shows you those points of intersection, which we need to set up our integral. You can find points of intersection through your graphing calculator as well. You just have to hit the second trace button and it gives you that intersect option. I'm sorry I'm not showing you this. I'm not actually on my laptop. I'm on a loaner laptop because mine is out for repair. So I don't have the graphing calculator on this loaner laptop. So I can't show you what I'm talking about. Sorry about that. I did sketch a quick picture for you. So pause the video so you can get the sketch in your notes as well. We're looking for the area between our two curves as x goes from 0 to 4. We're going to take the curve that is furthest away from the x-axis, the square root of x plus 3, and we are going to subtract the curve that is closer to the x-axis, 1/2 x plus 3. Closing that first parenthesis and dx. This one we can simplify a little bit before we integrate. The square root of x does not have any like terms. I am subtracting 1/2 x, and when I distribute the subtraction sign, this 3 also becomes negative, which cancels with my positive 3. Integrating, that square root of x is x to the 1/2 power, so I'm going to add 1 to the power and multiply by the reciprocal, adding 1 to the power of x and multiplying by the reciprocal of 2, I'm going to get 1 over 2 times 2, which gives me 1 over 4. Subbing 4 in for each of these, let's remind ourselves of how to evaluate a rational exponent. The denominator is the root, so this is saying the square root of 4, which is 2, and then cubing it. 2 cubed gives me 8, and then 4 squared is 16. 16 divided by 4 is 4, and again, subbing in that 0 to both terms, I still get a 0. This one you could use your calculator for. We have 16/3 minus 4, but 16/3 minus 12/3 gives us 4/3 unit squared for that area between the two curves. Now we're going to take a look at finding the area using the y-axis. So we've got our two equations here. We've got x equals 2 minus y and x equals y squared. I've got these entered in on Desmos for you again. We're going to take a look at these graphs. For the y-axis areas, we need to take a look at the y values where these graphs intersect. So our first y value is -2, and our second y value is 1. So our definite integral is going to be as y goes from -2 to 1, and then the first curve will be the one further from the y-axis. So we're going to start with our red line, which in this case was the x equals 2 minus y, and we will subtract the blue curve, the x equals y squared, from it. Once again, pause the video so you can get a sketch of our graph. We're finding the area as y goes from -2 to 1 of the curve that is further from the y-axis, which was our 2 minus y curve, minus our y squared curve, or the curve that is closer to the y-axis. And this time we're integrating with respect to y. This equation cannot be simplified, so I'm just going to go ahead and integrate. The integral of 2 in this case is 2y, because we are integrating with respect to y. For our y, we are going to add 1 to the power, multiply by the reciprocal. For our y squared, we are going to add 1 to the power and multiply by the reciprocal. This time our integral was from -2 to 1. Again, those y values. Subbing 1 in, we get 2 minus 1/2 minus 1/3 minus parenthesis. Here's where that gets very important. We're not subbing 0 in this time, so we will have to be careful with our negative signs. -2 times 2 gives me a -4. Squaring -2, I get 4 times -1/2 is -2. Cubing -2, I get -8 times -1/3 is a positive 8/3. This one really isn't too bad using mental math, although I know most of you don't love fractions. So at this point, if you just punch it in your calculator, that's fine. We get an area of 9/2 square units. And here's our last example for this one, taking a look at those graphs on Desmos. So here's the first equation. If you're not sure how to get fractions in on Desmos, all you have to do is hit the divide by button and it automatically turns it into a fraction. So of course the red curve is that first one, x equals 0. That was g of y equals 0. X equals are our vertical lines, and then the other bound for this one was y equals 3. So we're looking at this tiny little triangle section here, and we need to find where those curves intersect. Now it's okay that that x value is ugly. Remember, we're integrating with respect to y. So that is a very nice y value, y equals 3. And then here's the other point where those curves intersect as well. Once again, I have the graph sketched for you. Our y values, they intersected at 3 and 0. So go ahead and pause the video and get that graph sketched. Setting up the area under our curve. We're going along the y-axis. The curves intersected at 0 and 3. The function that is furthest from the y-axis is the red function, or our y over the square root of 16 minus y squared. Now remember, we are finding the area of this region here going along the y-axis because that was one of the equations we were given is x equals 0. So that curve closer to the x-axis was x equals 0. Of course, subtracting 0 doesn't do anything, so we can simplify this. And this function is doable to integrate by hand. However, some of them on the assignment I said you could use a calculator for, and this would be one of them. I want you to focus more on setting up the integral than on the integration itself. So the simple integrations I'll have you do by hand. The more complex ones I'll have you use your calculator. Again, sorry I can't show you this to remind you, but I think the majority of you are comfortable with this. At this point, you go into Math 9, and that's the definite integral option. You put in the bounds and the function, and you get an area of approximately 1.354 square units. All right, let me know if you have any questions, especially setting up those y ones. It's tricky to think about it in terms of y when we've been practicing in terms of x for so long. Take care.